All right, so when you start looking at this first problem, I need you to zoom out and just look quickly at it, because you should be able to say yes or no to a few of them without really even doing any math. So take a look at these 5, A, B, C, D, and E, and you should be able to say yes, 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 or no to a few of these without even looking at them. In fact, you can even classify a few of them by just looking at them. I'll give you 30 seconds. Use your brain. All right, so let's real quickly talk about this. If it's a triangle, remember our triangle inequality rule. The sum of any two sides has to be bigger than that third side. Now, if I'm assuming that this is already my largest side, I know that that is a reality. So when we were doing the inequalities where we were having an x and we were coming up with a range of values for x, that's when we don't know which is the biggest or which is the largest. We don't know. We need that range of x. Where does x fit in with respect to the other two sides? When I'm given all three sides, it's an easy conversation. Is 8 plus 5 bigger than 10? That's all you need to know. Are the smaller two sides sum bigger than that third side? That's your only inequality that you have to worry about. So when we start talking about, can I make a triangle out of, are these two sides, when I add them up, bigger than this third side? Because 13 is bigger than 10, yes, it is a triangle. Because all three sides are a different length, I know that it is definitely scaling. Because 1 plus 12 is bigger than 12, yes, it's a triangle. And I know right away it's isosceles because of those angle measures. So when I'm classifying them by sides, that's easy. Classifying by angles, I don't know. If this is a 1 and this is a 12 and this is a 12, if I sketch this triangle, I'm pretty sure it's going to be an acute isosceles, but I don't have that answer yet. So can I classify this by angles? I don't think so. Can I classify this one by angles? Not until we have today's lesson. And that's going to be an interesting conversation about what happens, because unless I have some kind of rules, I don't have any kind of rules that talk to me about how to figure out other than me just sketching and guessing. And sketches and guesses are fine for inductive reasoning, but sketches and guesses are not fine for Euclid's geometry, where we have to have a deductive, solid, sound method for all of our triangle figuring out. All right, let's talk about this one. 8 plus 12 is equal to 20. 20 is less than 21. So no, this one is not a triangle because the sum of my two smaller sides is not bigger than that third side. Make sense to you? All right, did we all skip the same one? You're like fractions. Oh no. Hey, it's about time you learned how to use a fraction. 1 divided by 2 is that decimal. 1 divided by 3 is that decimal. 1 divided by 4 is that decimal. We know that the bigger the number in the denominator, the smaller the fraction. I have an interesting quote on the outside of my room about that idea. So read that on your way out to lunch and back again. But if I need to know which two sides are my smaller two sides, here they are. So that math is going to look like this. 1 divided by 3 plus 1 divided by 4. Guess what? Your calculator knows your order of operations. And your calculator is going to divide this fraction first, divide this fraction second, and then add those values together. Now, I know that 0.58 is going to be bigger than 0.5, which is what 1/2 is equal to. So then I can right away say that yes, this is a triangle. Or therefore, yes, this is a triangle. And of course it's scalene because all of the side lengths are different. And again, no, I can't do the angles. Questions on these 5? All right, let's turn the paper over and jump in. Solve for each of these missing angles. Ask yourself, what do I see? What do I know? What do I need? And then classify those triangles by angles inside. And then I want to know if you can list them in order from shortest to longest. I'll give you a couple minutes to think. All right, check your work with mine and see if you agree with my thinking here. I know this is isosceles. So because it's isosceles, this is 62 and this is 62. 62 plus 62 subtracted from 180 gives me 56 here. There's a right angle, so I know these two are complementary, so I get 34. These two are a linear pair, so I can do 118. I could have also done 56 plus 62 is 118. And then angle B is going to be equal to 118 plus 34 subtracted from 180. Are we good on all those angle measurements? Were you able to get them all? ABC is an obtuse scalene because of this angle here. And my angle measurements are all different. ACD is an acute isosceles because of these two angles here make it isosceles, these two sides. Everything's less than 90 degrees. And ABD is a right triangle. And because A and B have different angle measures, I know that it's scalene. So those 3 vocabulary words for each category need to be in the front of your brain. Acute, obtuse, and right. And then isosceles, scalene, and equilateral. Can you list the sides in order from shortest to longest in the figure? So when I talk about ACD, I know that this is my smallest. And I have these two 62-degree angles lead me to these ones being bigger. But I gotta tell you the truth, so I don't know if this is smaller than whatever's going on here. So the best I can do is list each triangle separately. For ACB, I know that AB is my longest. And then I know that this is shorter than that, but I don't know where this compares with this guy. So in order for me to put them together, I can't. Like, remember we had that composite figure where the one side was the longest of one triangle and the shortest of the other triangle, so we could say how that meshed in. We don't have that situation here. So I can list them for individual triangles, but I don't necessarily know where they fit in to comparison with each other. Sound okay? All right, check out your homework from last class. You had a quiz review Go ahead and share your ABC answers with your group mates. Let me know ones you want to talk about. I'm super excited because we had the highest homework rate completion that I've seen in a long time. So woohoo, way to go. That means you're prepared for the quiz. How did the math space go? Yeah? It should have been easy.
There was, on the math space, there was one that had like isosceles, equilateral, stuff like that, and one of the triangles was an equilateral, but it wanted you to say equilateral and isosceles. Why is that?
Because an equilateral triangle is a special kind of isosceles. Just like geometry is a special kind of math class. So is it a math class? Yes. But for our purposes, when I ask you to classify that equilateral triangle, I'm asking for the most specific, so you're fine with calling it equilateral. Does that make sense? Okay. All right, if there's any other math-based issues, let me know and I'll pull it up and we can talk about it. All right. Given two sides of a triangle, what could be the third side? This one. And it's so important. They love giving you the values if it's equal. So they love this kind of an answer. Especially because your generation of SOL and multiple choice testing has you choosing all that apply. So it's not just the one answer. So I get a lot of kids circling all of them. 4 and 18 would not give you a triangle. I could pull out my sticks to remind you of why, right? Because if the two sides are 7 and 11, if I had a side that's worth 4, then that means that 4 plus 7 is equal to 11. So it's not going to be able to make a triangle. Okay, so 1 is B, 2 is C, 3. I like how this question's worded because we can see, here's my range of values. It can't be 22, it can't be 62. So all of those values are not possible lengths, so I have those ones in between. Ordering the sides from longest to shortest. 5, 6, 7, and 8. Check your answers with mine. Two sides of a triangle which cannot. Oh, I answered it backwards, didn't I? I missed the not, right? Which cannot be the length of the remaining side. So it cannot be 6. So that's the right answer. I hate those not questions. Anybody with me on that? Are we good? Which angle measures the least? Which could not be the length? And then there's John making a garden. Any questions on the first page? Are you good? I heard a wait. Are we good? All right, next page up. Classify each triangle by sides. Can you read them out loud so you get used to saying the words? On your mark, get set, go. What is it? Two isosceles. Read this one out loud. Yeah, and we want to get used to, and Charlotte, this is a good one. If somebody calls that an isosceles triangle, it is, just like this is math class. But the better name for this class is geometry, and the better name for this triangle is an equilateral triangle. And then it's also equiangular. We want to say it's an acute triangle. Don't say acute because we have a better name. So it's equiangular. We want to say that instead. All right, check out this figure. I have this exterior angle. So there's two ways of doing this. The sum of the two remote interior angles is equal to your exterior angle. So I went ahead and solved for y, and then I plugged in those values. You could have said that you could have done this supplementary math first, and then you could have said that this plus this plus this is equal to 180. Same difference, you're going to get the same value for y, and that is an acute scalene triangle, where you list the angles and sides from least to greatest. There you go. And then for number 3, because it's isosceles, these two are both worth the same value. So it's twice 5x plus 10 plus 40x plus 10. I get a value of 3 for x. And then I can plug in and figure out that it is an obtuse isosceles triangle. Down here, again, those conversations about which of the following sets of sides could represent a triangle. I take my lower 2 values. 13 plus 5 is 18. 18 is not going to be long enough. It's too short. My ends are not going to connect. So that's not going to be a triangle. I take my lower 2. That's going to be greater than my other side, so I'm okay. And that's an isosceles triangle, so that's not a problem. This one is an isosceles triangle, and it is a big problem. Because 1 plus 1 is equal to 2. So if I add those two sides together, it's going to be the same exact length. Think about those sticks that's lying on top of each other. That one's not going to be a triangle. 5 plus 6 is greater than 7, so yes, it's a triangle. How we doing? Feeling good? So we're going to start with the quiz. Awesome. When you finish with the quiz, you're going to pick up this worksheet here, which is a Pythagorean theorem review. So I want to talk about it real quick so you know what it is that you're doing. When you finish with the quiz, you're going to pick up this Pythagorean theorem review. And like I said, this should have been a review. In every triangle, the square of the length of the hypotenuse is equal to the square of the other two sides. So we have 2 samples for you to study. One where my missing side is the hypotenuse, and one where my missing side is one of the side lengths. And I want you to take a look at how to solve these. And then we have some practice problems for you here, solving for what's missing on each of these diagrams, looking for whether or not you are solving for a leg or one of the a hypotenuse. Remember, your hypotenuse is always going to be the longest side opposite of the right angle. So when you're solving for your hypotenuse, you're squaring the two sides and adding them together and then taking the square root. If you're solving for the side length here, this is one of the legs, you have to put this longest side, this is your C. So that's what you're going to work on and pick up after the quiz is done. Sound okay? Fabulous. So you'll notice during lunch I passed out the note sheet for today. This is actually a pretty quick note sheet. My plan is for us to scoot through this and let you get started on your homework, because wouldn't that be great? So we want to go ahead and talk about and make it official, the Pythagorean theorem. It's one of the hardest things to know when to introduce into geometry because you've kind of been doing it for years, and we're going to talk more about all the different cool parts of the Pythagorean theorem as we move through this chapter, and when we get to our next chapter on right triangles. That's pretty cool too. 2 chapters from now. Anyway, all right, so the Pythagorean theorem, and as we talked about in the very beginning of the year when we talked about Pythagoras, Pythagoras was like this hippie of the mathematicians. He studied under Euclid, and he was it Euclid or Eratosthenes? Anyway, and he was like this young guy with all these amazingly cool ideas. So this concept of the square of the hypotenuse is equal to the sum of the squares of the two sides, that's actually not new. The Egyptians were using this idea to build their pyramids and such. But what Pythagoras basically did was he was so into studying the number patterns. This is a very famous right triangle proof, where if you have a side that is 3 units and you have a side that is 4 units, if you square those sides, you get 1, 2, 3, 4, 5, 6, 7, 8, 9. You get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 as the square, the number of units. And what Pythagoras explored fully is that if you take each of those units, here's my 1, 2, 3, 4, 5, 6, 7, 8, 9 red, and my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, you can add them together and you can see that the sum of the squares is equal to the square of the hypotenuse. Some fun facts. A U.S. president, there are more than one ways to prove the Pythagorean theorem, and one of our U.S. presidents discovered his own theorem. Go ahead and Google it and let me know if you know who it is. Here's our little story about Pythagoras. He didn't actually discover this truth. He learned it from the Egyptians. If you watch this, and I'll put this link on Schoology for you, it's a funny video about Pythagoras and his love of beans. I'm not making that up. And then we can talk about what Pythagoras actually did spend a lot of time studying. He was obsessed with Pythagorean triples, and a Pythagorean triple is when all 3 side lengths are counting or are natural numbers. So if you remember our real number diagram, we can have irrational and rational numbers. Within rational numbers, we can have integers and whole numbers. Our counting numbers, or our natural numbers, are 1, 2, 3, 4, 5, whole values, not including 0. So we'll talk about which ones are triples as we move on. Here's the new part, and this is what is new to us. We've been using the Pythagorean theorem, saying if this is a right triangle, then this story is true. Geometry introduces us, of course, to the converse, meaning that we can use this relationship and we can use that to prove right triangles. So we're saying if, we say that if this is true, then this is going to be a right triangle. So instead of saying, hey, we were given a triangle that was right, and now we know this is true, now we can use this opposite conversation and say, if you have this relationship where c squared is equal to the sum of the legs, then you can go ahead and boldly say that that is going to be a right triangle. So the really cool part that we kind of alluded to earlier in our warm-up is, can you classify a triangle with given only the sides and no, or given only the sides and no angle information? Can you classify it according to angles? And the answer now is yes. We did not have this information an hour ago, but right now we do. Because if c squared is smaller than a squared plus b squared, it's an acute triangle. If you square the longest side of the triangle and it's bigger than a squared plus b squared, then you can say that's obtuse. So now you have your 3 choices. If c squared is equal to, then it's right. If it's smaller than, it's acute. If it's bigger than, then it's obtuse. And here's the deal. We on purpose talk about things in reference to just C. And I'm going to show you this little experiment right here. And this is why, so if you could look here at me. Here we have our thumb and our forefinger. And if this is a right angle, then I know that this distance that would make it a triangle is perfect. So if c squared is equal to a squared plus b squared, then I have a right triangle. And see how this pen just happens to naturally fit perfectly in my triangle that I'm making? If c squared is smaller, everyone okay with this golf pencil being smaller than my pink pen? If c squared is smaller, what kind of triangle do I have? If c squared is smaller. Do you see the cute little triangle? If c squared is smaller, then I have an acute triangle. Okay, which one's bigger, my pen or the pink pen? If c squared is, stretching my finger out. If c squared is what? Bigger, what kind of triangle do I have? Yeah, so you have not one but two little triangle testers. Because if c squared is equal to this distance, you have a beautiful right triangle, no problem. If c squared is smaller, so you can kind of play with your different lengths because here we have something that's smaller. This is c. So if you always make it about c, if the value of c squared is smaller than a squared plus b squared, what kind of triangle do you have? So you can kind of play with your pens and have that make sense. But when you're talking about this distance here, c squared being bigger, then I know I have an obtuse triangle situation. If I have c squared and c squared is smaller than the sum of the two squares, then I know I have an acute story. Okay, so let's jump in and get some of this practice done. If I use a Pythagorean theorem here to solve for x, now we have this conversation about leaving your rational values as simplified radicals, and you're like, wait, what? You should have learned how to simplify a radical in algebra. If that's not a true story, we'll continue to go over it with you asking questions until you understand. Here's the first thing you need to know. My hypotenuse is the side opposite of my right angle. So if you need to do like Maria and Maddie and take the time to make sure you understand which is the C side, that is my hypotenuse. And that helps you make sure that you write your formulas. X squared plus 15 squared has to equal 20 squared. 8 squared plus 12 squared has to equal x squared. 10 squared plus x squared has to equal to 21 squared. All right, do me a favor and go ahead and solve for those missing triangle sides, and we'll check back. If you are somebody that needs help with the calculator, let me make sure you know where the buttons are that you need to be touching. If you want to square something, this button here is the fastest and easiest way. So 20 squared adds that squared, and then pressing enter gives you the value. If you need to take the square root of something, that's this button here, second square root. And when you press that, you can take the square root of a value and it'll give it to you. All right, so we're going to talk first about 175 when I go to take the square root of that value. First of all, I know that 20 is my hypotenuse, so he's over here. X squared plus 15 squared is equal to 20 squared. So 400 minus 225 is 175. When I take the square root of each side, if I estimate and round it to the nearest hundredth, I have 13.23. We really want to make sure that we understand that simplifying of a radical. When I take 175 and I use my divisibility clues, I know it's not divisible by 2, but it is divisible by 5 because it ends in a 5. When I break 175 down into 5 and 35, I can break 35 into 5 times 7. Here is a double factor. I can write 175 as 5 times 5 times 7. When I'm taking the square root, anything that's a double factor can come out of the radical sign, and that gives me a value of 5 roots of 7. So that really is the best answer. This is an estimate. This is the actual true value. If this double factor doesn't make sense to you, let me explain to you it to you another way. 175 is 25 times 7. We got that up here. I'm allowed to split my factors under my radical. 25 times 7 is the same thing as the square root of 25 times the square root of 7. This I can simplify to 5. That's why the double factors. So we're going to call this 5 roots of 7 no matter how I got it. Make sense? Okay. So push yourself to continue exploring simplifying the radicals, and I'm hoping that it starts to make sense. All right. So for B, I have here 8 squared plus 12 squared is 208. So I know that 208 is equal to x squared. I can take the square root of each side. That's a property of equality. So x is going to be equal to, if I ask myself what is the square root of 208, 14.42. I'm going to round it to the nearest hundredth. And I make these squiggly lines to let everybody know that that's a rounded value. Let's go ahead and simplify the radical and see if that makes sense to me. 208, I know right away it's an even number. So when I take 208 and I divide it by 2, I go ahead and I get 104. 104 is also even, so I'll divide that by 2, and I get 52. Let me do this way. I'll go ahead and divide 52 by 2, and I get 2 and 26. I'll divide 26 by 2, and I get 2 and 13. Here's one double factor. Here's another double factor. So I know that 4 can come out of the radical sign because I have 4 twice, 2 sets of 2, and 13 is left inside. All right, let's take a look at the next one. 100 plus x squared is equal to 21 squared, 441, which means x squared is equal to 341. And when I take a look at 341, I'm not sure any divisibility. I can go ahead and try to divide by 3. It doesn't go in evenly. 341 divided by 7, it doesn't go in evenly. Another quick way to check it is to go up here and ask myself 341 divided by all the numbers in the whole wide world. Go to the table of values. Oh dear, my calculator was set on something. Hold a minute. Let me clear it out. And I can do 341 divided by all the numbers in the whole wide world. 1 goes into it evenly, and 11. So it's not prime, but it's not going to be able to be simplified. So my x has a value of the square root of 341. I can go ahead and estimate that value. Square root 341 is about equal to 18.4, round up to 7. All right, so then this question here, which of the right triangles above have values that represent Pythagorean triples? And a Pythagorean triple, remember, is all natural or counting numbers. If you don't know what that means, no fractions, no negatives, and obviously no 0, because you can't have a side length of 0. So if you look here, here's a radical, here's a radical, there's a radical, so none of those values above. represent Pythagorean triples. All right, check out A, B, and C. What we want to do is check out, this is definitely our C, which is our longest. This is our C, which is our longest side. I think so. Let's check out this value, 4 times the square root of 35. 4 times square root of 35. Yeah, that's definitely the longest. So we're going to check out and see what is the relationship between 89 squared, and I'm going to go ahead and put a question mark in here when I compare it to 39 squared plus 80 squared. Is it equal to? Is it greater than? Or is it less than? Because if C is smaller than, it's going to be an acute triangle. If C is greater than, it's obtuse. If C is equal to, it's right. Let's check this one out. 4 times the square root of 35 squared. How does that compare to 20 squared plus 13 squared? Here we need our biggest side length, which is here, 52. How does 52 squared compare to 28 squared plus 4 times the square root of 2 squared? With your partners, talk about A, B, and C, which are acute, which are right, and which are obtuse. Go ahead. All right, so if I have 39 squared, and I'm going to add that, 39 squared, make sure you arrow out, plus 80 squared, that has a value of that, 89 squared. Uh-oh, what kind of triangle is it? Once I know it's a right triangle, because these are equal, I know that's a right triangle. All right, let's talk about B. When I go to try this one, I'm going to take 20 squared, and I'm going to add it to 13 squared. I get 569. Parentheses, 4 times the square root of 35 squared. Oops. Darn it. I was trying to get it so you could see it. 4 times the square root of 35. Arrow out. Close your parentheses to the second power. That's how we want to make sure we enter that one into the calculator. Oh, what kind of triangle is it? It's acute because C is smaller, so it's going to be an acute triangle. If you want another way to enter this into the calculator, you can go ahead and take the square root of 35, and then you can square that. Ah, no surprise. Times 16, which is 4 squared. You get the same value. All right, let's talk about this one. 28 squared, arrow out, plus 4 times the square root of 2, arrow out, close parens, square it. 52 squared. Oh my goodness, much bigger. So guess what? This is much bigger, but now what we need to do is, do we even have a triangle? Because when you get an obtuse triangle that's so wide and so big, there's a chance this isn't even a triangle. So I need to say, is 28 plus 4 times the square root of 2 even a triangle? No, that's not even close to 52. This one is not a triangle. Crying real tears over that one. So don't forget, when you're doing your, whether it's acute, right, or obtuse, if you get an answer that's crazy off, go back and check to see if it even is a triangle. That's a great way that they like to try to trick us. Good news is we're smarter than that.